Hello, this is Professor Zaman. Welcome to Hasan Zaman educational video series. In today's video, we will learn how to solve circuits with current sources using mesh analysis or loop analysis. In a previous video, we have learned mesh analysis or loop analysis for circuits with only voltage sources. But today we will learn the same technique for circuits where there may be current sources as well. There could be both current sources and voltage sources or just current sources. In either case, we will be able to apply this technique that we are going to learn today. Let's begin. The mesh current or loop current analysis with current sources or super mesh. Some people also call this technique super mesh technique. Regardless how we call it, but the technique is same. If you look closely, you can see that it is possible in this circuit to convert this current source into a voltage source. In the previous videos, we have learned how to do that. I am going to redraw the circuit by converting this current source into a voltage source. So if you remember, to convert a current source into a voltage source, you have to put this parallel resistor in a series configuration with the voltage source. And the value of the resistor remains the same, 6 ohm. And the value of the voltage source becomes multiplication of this resistor value and this current source value. That is 6 times 6, 36 volt. Okay, so this is our equivalent circuit to this circuit. We just converted the current source into a voltage source. But if you have seen the previous video where we have learned mesh current or loop current analysis, you will be able to see that this is the same circuit that we solved in that video. So now we understand we can solve most of the circuits with current sources using this technique, that is to convert all current sources into voltage sources, then apply the usual technique of mesh current or loop current analysis. But this is just a choice. You can do this way, or you can choose to solve the way the circuit is without converting the current sources into voltage sources. Actually, that will be required in some cases, because in this case we have a parallel resistor with the current source. So we can convert this current source into a voltage source. But there will be circuits where there will be no parallel resistor with the current source. So you will not be able to convert them to voltage sources. In that case, you have to use the technique that we are going to learn today, that is solving circuits with current sources using mesh analysis or loop analysis. So let's try to solve this circuit keeping the current source as it is. We first assign loop currents. Now we have to assign the polarities to all voltage drops and rises. In this resistor, current is flowing this way, I1, because this is a non-shared branch. So current will be I1. So this is the direction of voltage drop. The current in this branch is I1, just like the loop current, and current in this branch is I2. Current into this branch is I3. Now The currents in the shared branches are found by combining the currents in the adjacent loops. For example, in this branch, if we assume it's downward, the current is I1 minus I2 because I1 is flowing downward and I2 is flowing upward. Also, you can find the same value if you apply KCL at this node. I1 is flowing in here, I2 is flowing out. So this current will be I1 minus I2. So that's the beauty of mesh current analysis. You are assuming this current I1 minus I2, which is found as a combination of these two unknowns. So you are not introducing a new unknown like I3 or I4. So you have fewer variables to solve for. We assign polarity like this. The current is I1 minus I2. But when you consider this loop, we'll assume current is upward. So it will be I2 minus I1. We explained this in the other video. Because current here is I2 and current here is I1. So the upward current must be I2 minus I1. So for I2 minus 1 upward current, we're going to write the polarity like this. And for this resistor again, when you consider the current is I2 minus I3, it will be plus here, minus here. And here in this loop, we will consider the current is I3 minus I2. So plus here, minus here. So we are done putting the polarities for all elements in the circuit. We only haven't done that for this element, the current source, because we do not know the voltage drop across it. We only know the current through it is 6 ampere. Now let's write down the KVL equations as we do for mesh current analysis. So for this loop, if we start from this node, we go clockwise, it's plus 96 voltage rise. Here it is minus 4I1. It's a drop. If current, we're considering current is I1 minus I2, so it is a drop this way, so minus 12. I1 minus I2. And we have come back to the starting point, so equal to 0. So this is our first equation. Now for this loop, we start again at the ground node and go clockwise. Here we will consider the current is I2 minus I1. So this will be the polarity or voltage drop in the upward direction. So it will be minus 12 I2 minus I1. Here no drop, and here it is minus 6 times downward current here is I2 minus I3, 6 and we have come back to the starting point, is equal to 0. We got two equations, but we have three unknowns, so we need another equation. And our natural instinct will be to write another KVL equation in this loop. But we will not be able to do that. Let's try it first. So let's begin from this bottom ground node, which the whole thing is a ground node here, and go clockwise. So here we have a drop. If you consider the drop on the right side, that is current is I3 minus I2. This will be I3 minus I2. Now here we don't know the voltage drop. So what do we write here? We actually cannot write this equation. We cannot complete this equation. So we have to use a different technique. Before I do that, I would like to remind you one thing. That is why we are doing this thing. Like on the left side, plus at the top, minus at the bottom. On the right side, plus at the bottom, minus at the top. The only reason is, in these equations, we want to have all voltage drops in the resistors as negative quantities. You see, this is a voltage drop, negative, negative, negative. But only this is positive because this is a voltage source. We cannot change that. But all voltage drops in resistors in these equations will come out as negative quantities. So there will be less chance of making a mistake. And this is also more systematic. You always write the loop current first minus the neighboring currents. But as I said in the previous video where you first learned this technique, if you didn't like this, if you chose, no, I will use the current I1 minus I2 here downward, you could do that. If you choose the left side, your equation will be plus 12 times I1 minus I2 because current is downward, and which is same as this one. If you put the minus inside, it will be I1 minus I2. So that will be nothing new. Let's come back to our problem. That is, we need another equation, but we do not have an equation. But actually, there is an even easier way here to get the third equation. The way is, wherever you will see a current source, you will know eventually you will get one less equation. For example, for this current source, we are not getting this equation. But each current source will give you also a different equation, actually easier equation. That is, if you look here, I3 is flowing downward, but the current in this current source is actually upward, 6 ampere. So what will be the value of I3? I3 is clearly minus 6 ampere. So instead of writing this KVL equation, we can simply write I3 is minus 6. So now we got our three equations and we can solve them and we'll find all the currents. So this is actually easier in a way. A question might arise like, how would you know which KVL equations you should write? In this case, this current source on the side, so kind of easy to understand, but sometimes the current source might be in the middle. Then what do? The technique is, mentally you have to assume that this current source is not there. So for a moment, let me remove this current source. Okay. Now you see, this loop is not complete. Only loops you are left with, this loop and this loop. So if you mentally remove all the current sources, you will be left with some loops, and you have to write KVL equations only for those loops. In this case, this loop and this loop. Because in this loop, you do not have a complete connected path, so you do not have to write this equation. But you will immediately know that you will get a different equation, not KVL, actually, which will be an easier equation like this one for each current source. So again, the rule of thumb is, for solving circuits using mesh current or loop current with current sources, you will always get one fewer equation or one less equation for each current source. In this case, we have one current source, so we got one less equation, less KVL equation. But each current source will also give you an extra equation to make up for that. So let's solve these equations. From equation 1, 96 equal to 0, minus 16 I1 equal to minus 96 4 I1 minus 3 I2 equal to 24. So this is our new equation, equation 4. Now from equation 2 and 3 together, minus 12 I2 is equal to 6. This is our fifth equation. Subtracting 5 from 4, so I1 is 9 ampere. So I2 is equal to 4 ampere. Let me put it back, the current source, because it is in the circuit. So we have solved the circuits. Now we can find all other currents and voltages in this circuit. For example, I1 is definitely 9 ampere, I2 is 4 ampere, and I3 is given already, minus 6 ampere. And the branch currents are, this branch current is I1 is 9 ampere, I2 is 4 ampere, I3 is minus 6 ampere, and this shared branches current downward will be I1 minus I2, that is 9 minus 4, 5 ampere, and this shared branches current downward will be I2 minus I3, that is 4 minus 6, so it will be actually plus. Let me show it here in this box. 4 minus 6 is equal to 4 plus 6 is equal to 10 ampere. So this current will be 10 ampere. You will find the same thing if you had used KCL at this node. This current 4 ampere is coming in here, and this current is 6 ampere this way, because this is minus 6 current this way, actually 6 ampere, and those two will combine and come through this branch, which will be 10 ampere. Now we can find all the voltage drops. For example, this voltage drop will be 4 times 9, 36 volt, and this will be 5 times 12, 60 volt. This will be 10 times 6, 60 volt. Another important thing to notice here, since these two branches actually are in parallel, so both have 60 volt drops. Parallel branches have always same voltage drop. Another question may arise, what is the voltage drop across this 6 ampere current source? That is also 60 volt, because all three of them are in parallel. So by solving this circuit, when we found these voltage drops, now we also know the voltage drop across this current source, which is also 60 volt. Now we will look at a situation where you cannot convert the current sources into voltage sources. In this circuit, as I mentioned at the beginning, you could have converted this current source and this resistor into a voltage source and a series resistor, and that would have given you the same circuit that we have solved before in another video. But you may not be so lucky. In some cases, you will not have a parallel resistor with the current source. In that case, you cannot convert this current source into a voltage source. So that means in that case, you have to apply this technique. And this technique, as I mentioned earlier in the video, that some people call super mesh, is kind of like a bigger mesh. And that naming will make more sense when we do the next circuit. So let's draw a circuit somewhat similar to our last circuit with some changes. And let's call it 4 ampere. We have two voltage sources and two current sources. And if you look carefully, you will see we cannot really convert these current sources into voltage sources. Let's take this one. This current source doesn't have just a resistor in parallel. It has a combination of things which are not suitable for converting it to a voltage source. Similarly, on the right side doesn't have a parallel resistor either. And look at this current source. It doesn't have a single parallel resistor. So in this circuit, we cannot convert any of the current sources to voltage sources. So we have to use the same technique that we learned in the previous example. Let's first assign the loop currents or mesh currents. So let's call this I1, I2, and let's call this I3. So we have three loops here, so we have to assign three currents. Now to write KVL equations, we have to mark polarities, here minus, plus, and when you are considering this loop, current is flowing this way, I1 minus I3, because this resistor is between these two loops which have loop currents I1 and I3. I1 is in the direction in this way, and I3 is the other way. But for this loop, we will assume direction of the current in this resistor is this way. So this I1 minus I3. So we will put plus on this side, minus on this side. But for the upper loop, current, we will assume current is I3 minus I1, and which is obviously this way. And for that, we will put plus on this side, minus on this side. And for this resistor, in this loop, current is this way, I2 minus I3, so plus here, minus here. And for this loop, current is this way, I3 minus I2, so plus here, minus here. And for a voltage source, we cannot change the polarity, so it will be plus minus. Now, for each current source, you will get one pure KVL equation. So even though there are three loops, 1, 2, 3, for this current source and for this current source, you will get two pure equations. That means you will actually get only one equation, one KVL equation. But those two equations will come from the current sources themselves. And to find out in which loop you have to write the KVL equation, I mentioned in the previous example that mentally you have to visualize that these current sources are not there. So if it's become difficult to visualize that, you can temporarily remove them. For example, this 2 ampere current source is removed, and this 6 ampere current source is removed. Now it is easier to see where we have a complete or closed loop. Only this loop, no other loop. This loop is broken because of this, and this loop is broken, this loop is broken. So we are left with only one connected or closed loop, and you have to write the KVL equation only for that loop. Let's start with the ground node, go clockwise, is plus 96. Here we will use the signs at the bottom, plus on this side, minus on this side. That is, current here is I1 minus I3, and it is a drop, 4 and minus I3. And what is the drop here? We again will assume this plus and this minus, because we are writing the equation in this loop. So minus 6. What is the current in this branch? This is the shared branch. Current in this direction actually here, I2 minus I3. Many students make mistakes here. They sometimes write either I2 minus I1 or just I2. You cannot make that mistake. You have to think what is the branch current here. The branch current here is this direction, I2 minus I3. 6 times I2 minus I3. Now here it is a drop, minus 36. And we have come back to the starting point is equal to 0. So this is our equation 1. And as I said before, we cannot have any more KVL equations. So I am putting them back, the current sources. I just took them away temporarily. So what is the branch current in this branch? This is the shared branch between these two loops, and current upward in this direction will be, this current is upward and this current is I1 is downward. So this upward current is I2 minus I1. You can also think in KCL way, current in this branch is I2, because I2 is the loop current, and current in this branch is this way I1. That means current here will be I2 minus I1 if we use KCL. But in a loop current way, with the way we think, I2 is in this branch upward, I1 is downward, so the net upward current is I2 minus I1. That is equal to 2 ampere. So that's our second equation. Now for this current source we will get another equation. What is the branch current in this branch? If we look at I3, I3 is actually flowing the same direction as the current source's direction is. So definitely I3 will be 4 ampere. So now we got 3 equations and we have 3 unknowns. We can easily solve it. So I1 is 7.2 ampere. (9.2 ampere). 4 ampere. Okay, so we found all 3 loop currents. So let's mark down the branch current. So this branch current is I1 is 7.2 ampere. So this is 7.2 ampere, and this branch current is I1 minus I3, which is 7.2 minus 4, it will be 3.2 ampere. And current in this branch has to be 2 ampere upward because this is a current source. And in this branch current is, this way is I2 minus I3, and I2 minus I3 is 9.2 minus 4, which is 5.2 ampere. And what is the current here? Is I2 this way. I2 is 9.2 ampere. So we have solved all the currents. Now the voltages is simply using Ohm's law. This is 96 volt and this is 4 ohm times 3.2 ampere. You will get the voltage drop here. And here 6 ohm times 5.2 ampere. You will get the voltage drop here. So that means we have solved this circuit. I haven't discussed one thing, why people call it super mesh. The answer is truly I don't know. But what my guess is, when we remove this current source and this current source, remember we are left with only one big loop here. It's like a mesh or loop of bigger size, super size. So that's why some people probably call it a super mesh. But it is not always true. For example, in the previous example, remember, when you remove the current source, the loop didn't really get bigger. But in most cases, you will probably have this kind of situation where current sources are inside the circuit. And when you remove the current sources mentally, I'm not asking you to remove them really from the circuit, just to visualize as if they are not there, so you know if I can find out which loop you have to use for KVL equation. So when you do that, that is, you remove the current sources mentally, you will be having a bigger loop or super mesh. That is probably the reason why people call it super mesh. So I hope I was able to remove the mystery around super mesh, which some students are afraid of. This is just simply a technique of solving circuits with current sources. Hope you enjoyed the video, and I encourage you to watch our other videos. Thank you for watching. Bye.